Hey, yeah, I have both of them open right now, waiting for it to start.
Alrighty, welcome everyone. We are now in week 6 of HuggingFace's Deep Reinforcement Learning course. This week we will be covering actor-critic methods with robotic environments. Um, if you haven't seen already, I am currently enrolled in competing in a pitch competition. If you check out whatever social media platform you're on right now, I'm sure you'll see a promotion from me to promote my startup company. I'm offering to give away thousands of dollars worth of value, and all you have to do is one simple task. If you're interested, check out my social and watch the video, and let's see if you're lucky, one of the lucky ones that'll win one of several prizes. So without further ado, let's begin.
Hey, your mics on Facebook and YouTube sound very quiet. You might be using the wrong one on them.
Good call. Let's go. All right. I just swapped it, so it should be better now. Thank you. Was it audible at all or no?
It wasn't that audible, but it's better now. I can hear it.
Okay, perfect. Um, so yeah, without further ado, let's just begin. So, introduction to actor critic. So this week we were introduced to the actor critic method. It's very exciting stuff, and we'll be exploring how these methods combine both policy-based and value-based approaches to stabilize training and improve learning efficiency in deep reinforcement learning, especially within robotic environments. Over here, this video is actually the agent that I trained, the A2C agent. In the It's a robotic arm, and it's tasked with picking things up. And you can see that there's a lot of kind of moving pieces and a lot of variables to keep track of. And I thought that overall, this is very cool to see. And with all of these deep reinforcement learning examples, we're really kind of working towards simulating the real world. At least that's kind of my intent when I'm learning deep reinforcement learning. I'm very interested in robotics, and I want to create intelligent robots that can do tasks, make decisions. And deep reinforcement learning, obviously you can see here, we're training in a kind of a 3D video game type of environment. But if you account for all of the possible like significant variables that you experience in the real world, like friction and like air resistance, gravity, you can simulate that in video game environments pretty easily. So training a reinforcement learning agent in a video game translates pretty well to that same representation in real life. So we all know like Google Aloha, they have a really powerful robot arm that can do a bunch of cool things, and we're working towards that, at least getting a peek into how that works in this week's course. So, understanding policy-based methods. Policy-based methods focus on directly optimizing the policy to increase the likelihood of actions leading to better returns. One such method is reinforce, which uses gradient ascent to optimize policy weights, but suffers from high variance due to Monte Carlo sampling. As a recap, this is from last week, I think. Um, this is the policy gradient equation. We see here that this, I had to look this up, the upside down delta, the inverted delta is actually called nabla, but we're approximating this policy gradient. And this is to simplify it, I'm only going to explain the one trajectory equation. Um, we were talking about how there's high variance due to Monte Carlo sampling. So this is taking it one step behind. Instead of having a high variance due to Monte Carlo sampling, let's look at if we just have one sample, one trajectory. So the estimation of the gradient, given we use only one trajectory to estimate the gradient, is equal to the sum of, over here, the direction of the steepest increase of the log probability of selecting action AT from state ST. And in red, you see that probability, this right here, this equation, this portion of the equation is the probability of the agent to select action at action AT from state ST given our policy. And here we have our cumulative return. So this is the policy gradient and simplified to one trajectory, and we'll see why this is important. So now, what is the challenge of variance in reinforce, the reinforced algorithm? So reinforced algorithm increases or decreases the probabilities of actions based on the return. However, due to the environment's stochasticity, this can lead to very high variance in policy gradient estimation, making training inefficient and slow. So stochasticity, this is kind of like the wide distribution of potential actions and state action pairs. The great way to depict this is we have our starting state, and this is the Pong environment. There are potentially multiple trajectories, multiple actions you can take in that state, but the return from a certain action in that state could potentially be this crazy array of potential numbers. There's all these possibilities. Maybe one trajectory, one action, one state action pair will lead to 100 reward. Maybe it's terrible and you get a -1,000 reward, or maybe it's decent but it's better than doing nothing. For example, you get a 10 reward, or just slightly bad at a -40 reward. So this is that stochasticity, this distribution of possible actions with associate, and we see here that each one of those trajectories has a potentially different kind of reward, and we're always optimizing for the greatest sum of reward at the end of the day with reinforcement learning. So the question is, how do we get to the 100 reward, and how do we have our agent train and reinforce this 100 reward action compared to all of these potential options? That's what we're exploring. That's the question. So now let me introduce to you the actor-critic method. So this is a really simple diagram of kind of comic that explains it. So actor-critic, think of there being two types of individuals or two people playing a video game. You have one guy, when you're learning a new video game, you have one guy that's kind of controlling the controller, and then you have another guy that's kind of either teaching you, maybe they know a little bit better or whatever. You're hanging out with your friend. So maybe you're the player. You can take control of the controller and do this action of rotate the piece, like when we're playing Tetris, and then you can have a critic that says, maybe don't do that. Try something else. And this is at a high level what we're trying to do with the actor-critic method. So the actor-critic method aims to reduce the variance issue in reinforce by combining policy-based actor and value-based critic methods. So up until this point, we have learned policy-based methods and we have learned value-based methods, and we're taking it a step further and combining the two for different components of that decision-making problem. So we used the policy-based as a policy-based method for our actor and a value-based method for our critic. The actor dictates the policy actions, while the critic evaluates these actions by estimating how good they are. This synergy aims to stabilize training by providing more consistent feedback. So in a nutshell, this is what the actor-critic method is and what it does. There's a specific type of actor-critic method called the advantage actor-critic, A2C. A2C is a specific type of actor-critic method that introduces the advantage function to further enhance learning efficiency. The advantage function helps in determining how much better an action is compared to the average, guiding the actor to make more informed decisions. So, on top of this actor-critic method, we now introduce this advantage function, which states that advantage, which receives state in action, is equal to the Q value for action A in state S minus the average value of that state. And as a recap, the advantage function helps in determining how much better an action is compared to the average, guiding the actor to make more informed decisions. So this is what separates this A2C method from a regular actor-critic method. So that was pretty much all of the coursework and reading material. A lot of it just kind of introducing these new concepts, but we're getting to see how we can plug and play these different methods to work in different environments and for different problem sets. So for the rest of this group study, I'll go over my work and the solutions to the hands-on environment. So we begin by, we're going to train in the Stable Baselines 3 and Panda Gym. So these are the dependencies. We will use Stable Baselines 3, a library for deep reinforcement learning, in combination with Panda Gym to train a robotic arm to reach a specific position. This hands-on approach will help solidify our understanding of A2C methods in practical scenarios. So this is taken directly from the workbook. You can see here that we're going to install these dependencies. It can take a while. For me, it didn't take as long. It says installation can take 10 minutes, but I only took 1 minute for the first install and then 58 seconds for the next one. So Panda Gym, it contains the robotic arm environments, and Stable Baseline 3, SB3, is a deep reinforcement learning library. So we're installing this and getting our dependencies within our environment. Now we have to set up the environment. We installed the dependencies, so now we have to actually set things up. So before diving into training, it's crucial to set up our environment correctly. We'll use Panda Reach Dense version 3 from Panda Gym, which simulates a robotic arm tasked with reaching a target position. This is exactly what we saw right here. This is that import, this environment. This setup will involve creating a virtual display for Colab, installing dependencies, and understanding the observation and action spaces. So you can see here, we define our environment ID. We're going to use the Panda Reach Dense version 3. We're going to create the environment, and we're going to get the state space and action space by calling the state size and action size. And over here, we are going to print what we see, and we can see that state space is none. This one kind of like the notebook timed out, but you would see what the size is, and some of the observations will be printed in the console. Next, we will normalize our inputs and rewards. So normalizing observations and rewards is the best practice in reinforcement learning to ensure stable training. If we don't normalize it, we could have like huge outliers that will skew our results and could potentially like lead to an early like failure or really unstable, non-replicatable runs. So we use vec normalize to standardize inputs and rewards, which helps in enhancing the learning process by providing the model with consistent and scaled data. So here we see we have to add a wrapper to normalize the observation and the reward. And to do that, we call vec normalize on our environment. We call normalize observations to true, normalize the word to true, and our clip observations to 10. With all of these, you would like call the function, and then what I like to do is whenever I get into the parentheses, I'll do a control space to see what are the parameters you can set. But this just shows you what the solution looks like. Next, we create the A2C model. We use SB3, and we'll create our A2C model, the Advantage Actor Critic model, specifying the multi-input policy for our robotic arm environment. This step is crucial as it sets the foundation for our agent's learning capabilities. So here, breaking out the code, we're tasked with defining the model, and the solution is we call A2C, which is the Advantage Actor Critic method, on our policy, and we set policy equal to the multi-input policy, the environment set to the environment we have above, which is normalize, and verbose equals 1, so we can see what are the intermediate steps. This is when, like you see here, using CUDA device, you will have to set a GPU in your runtime. You can do that locally, which is a little bit more complicated, but I used the Colab. You can do it for free, and just make sure you're using a GPU. Now that we have everything set up, we created our agent, it's time to train the agent. So training involves running our A2C model for a specified number of time steps. This process allows the agent to interact with the environment, making decisions, and learning from the outcomes. We aim to train the model to improve its policy for accurately reaching the target position with the robotic arm. So all you have to do once you have everything set up is run the model.learn command and how many time steps you want to use. This one for me took a while. They approximate 25 to 40 minutes of training. So whenever you do get up and to this point, you can take a break after you get your model running, and then you can take a quick peek to see, make sure you don't time out. You might have to restart if it times out, which is one of the big problems if you're on a free tier on Google Colab, which I definitely am. One of the big workarounds though is if you just have a bunch of Google accounts. If you time out on one, you can just swap out to the next and keep rinsing and repeating. So you got to do what you got to do if you're trying to ball in a budget, is what I like to say. And you can see throughout the training run, you'll have these printouts. So rollout, you have the episode length mean, episode reward mean, success rate, and just a bunch of other variables like time, iteration, FPS iterations, time elapsed, total time steps, train, entropy loss, explained variance, learning rate, number of updates, policy loss, standard deviation, and value loss. And that's kind of the printout from the console log for when we set it to verbose. This is why, so you can see how you progress throughout the training. So after you have trained your agent, it is now time to evaluate. Post-training, we evaluate our agent's performance to understand its efficiency and accuracy in the task. Evaluation helps in identifying areas of improvement and further tuning the model for better results. So here you can see we import dummy vec env and vec normalize, and we'll load our saved statistics. So eval environment, we're declaring eval environment is equal to dummy vec environment, and we're calling it on this array lambda of type gem make panda reach dense version 3. Then we'll vec normalize it and load that save from above. Vec underscore normalize that pkl, passing in the eval environment. We need to override the render mode. So eval env, we're gonna call on that object dot render underscore mode and set it to RGB array. We do not want to update them at test time, so we set eval env dot training to false, and we want to normalize. Reward normalization is not needed at test time, so we will set that to false. But we previously set these to true above. Now we load our agent, so we declare the model and set that equal to actor advantage critic, calling the load method and the name of our passing the name of the agent. We're going to destructure mean reward and standard deviation of the reward and set that equal to the evaluate policy with model, passing model and eval environment. And after all of that, you can print your results. And my results for this training run are mean reward is equal to minus 0.22 plus or minus 0.07, which is a pass for this environment and for the 1 million time step requirement in the HuggingFace course. So a lot of stuff to dissect, but conceptually, like we saw, there were not too many new concepts introduced. So we got introduced to the actor critic method. We did a recap on policy-based methods and specifically reinforce. We saw the challenges of variance when using the reinforce algorithm. We were introduced to the actor critic method formally and specifically introduced to the advantage actor critic method, which is a specific type of actor critic. And from there, we trained our robotic arm using that advantage actor critic method. So in conclusion, actor critic methods, particularly A to C, offer a powerful approach to tackling the challenges in deep reinforcement learning, providing a balanced mechanism for policy optimization. Our hands-on training with the robotic arm in Panda Gym serves as a practical example of applying these concepts. Next week, we got multi-agents. So this is the screenshot from next week's course. We're going to be doing AI versus AI in soccer. So that looks very exciting. With that, do we have any questions? You got any questions?
Uh, I don't think so.
Okay, cool. Well, thanks again for hopping on. We meet every Thursday at 10 a.m. Eastern, so make sure you catch us for the next one. We're nearing the end of our course, and we'll be looking to move on to another concept in deep reinforcement learning or artificial intelligence in general. It's always important to keep learning, continuously learning, and reinforce your learning. So, thanks again for watching. If you didn't catch that announcement at the beginning, I'm doing a giveaway right now. If you're interested in potentially winning up to $1,000, several thousands of dollars worth of value, make sure you check out the video that I have posted. I can get a link quickly, but thousands of dollars worth of value 2 weeks to you if you're lucky. And depending on where you're watching from, you can check it out. I posted it on Twitter, LinkedIn, Facebook. And if you're interested in potentially winning thousands of dollars worth of value, including $20 PayPal gift cards, all while supporting a colossal cause, which is healthy aging, longevity, then check out this video to learn more. So thanks again for watching. Have a good one. Peace.